Okay, welcome you all for today classes. In this today classes, we are going to uh, study the derivation of a general heat conduction equation in Cartesian coordinates and cylindrical coordinates. Okay, so we have derivations in this today classes. Okay, so first we start with the uh, general heat conduction equation in Cartesian coordinates, and that is in rectangular shape element. That is a rectangular shape elements are value. Okay, so there are some assumptions. We have to make some assumptions in while deriving the general heat conduction equation in Cartesian coordinates. Okay, so what are those assumptions? First one is the material is homogeneous and isentropic, so that whatever the material is there, that is the homogeneous material and it is isentropic. The entropy of that material is the same, and also it is made up of with the same material. Same material. The homogeneous is nothing but the material, whatever we consider that material is made up of with the same material. That's why it is called as a homogeneous material, and it is also a isentropic one. Isentropic one. This is the first assumption. Material is the homogeneous and isentropic. Second one is density of the material is constant. The density of our considered material is constant. Third one is the specific heat of material remains same. Cp value. Cp value of the material remains same. That is Cp value of the element is same. Okay. Temperature is the function of position and time. Temperature is the function of position and time. T is the function of position and its time. Okay. So these are some assumptions which you have made while deriving this general heat conduction equation. Okay. So let us start the real derivations now. Consider an infinitesimal rectangular volume of side dx, dy and dz parallel to three axes x, y and z respectively. So here consider this is the uh, x, y and z plane. Okay, so these are three planes, and within this plane you can consider one volume, that is infinitesimal rectangular volume. This is the rectangular volume which is having the sides. It is having the sides, that is, so here the dx and this is the dy and it is the dz. It is having three sides, dx, dz and dy. So all these three sides are parallel to this planes x, y and z respectively. So this dx side is parallel to the x plane and dz side is parallel to the z plane and dy plane is parallel to the y plane. Okay, respectively. Okay, let let kx, ky and kz is thermal conductivities along x, y and z axis. Let kx, ky and kz are the thermal conductivities along x, y and z axis. Okay, so next one is the Qg is the heat generated per unit volume per unit time. Let small Qg is the heat generated per unit volume per unit time. Okay, rho is the density of the material. Rho is the density of the material. Cp is the specific heat of a material. Cp is specific heat of material. So this is about the element information. Element infinitesimal rectangular volume element information. What are those? Dx, dy, dz are the sides which are parallel to the x, y and z planes respectively. Kx, ky and kz are the thermal conductivities along x, y and z axis. Small qc is the heat generated per unit volume per unit time. Rho is the density of the material. Cp is the specific heat of the material. Okay. Now let's start here. Applying energy balance for the volume element. We have to applying the energy balance to this volume element. So we have to make three terms by applying the energy balance to this volume element. What are those? First term is net heat accumulated in the element due to the conduction of heat from all three directions. The first term is net heat accumulated. When the heat is flowing from this side to this side, through this element and exiting from this side, as well as the heat is flowing from in y direction and exit from this direction. Similarly, the heat is flowing from z direction and exiting from this direction. So when the heat is flowing through this element, the net heat is accumulated within the element. That is our first term. That is, net heat accumulated is nothing but storage of heat. Storage of heat. When the heat is flowing, some amount of heat is stored in this element when it passes through this all these three directions. That is what our first term, plus heat generated within the element. That means uh, once first term is when the heat is flowing inside through this volume. So in that cases, some amount of heat is stored here. Another second term is heat. If there is a heat generated element is there within this element, if there is heat generated element is present in this element, then that is our second term. That is heat generated within the element. So that we have to consider it as a second term. Okay, and third term, that is this plus second term is equal to third term. That is energy stored in the element. So that is we have to consider third term, energy stored in the element. First is net heat accumulated in the element when we have to we apply the heat that is flow through this element in all the directions, and plus heat generated within the element, which is equal to energy stored in the element. Energy stored in the element. So we have to make three terms here. Okay. So next we have to go with one by one term. That is first term, the quantity of heat flowing into the element during the time interval t tau in x direction. Okay, the quantity of heat flowing within to this element with the time tau in the x direction. This is what x direction. Okay, so that we have to write here Qx is equal to, already we know that the heat conduction equation, that is minus Kx dy dz dou t by dou x into d tau. That we have to consider it as equation number 1. Okay, Qx is equal to, this is the heat conduction equation in x direction, that is minus Kx. Okay, this is thermal conductivity in x directions. Dy and dz is nothing but the area. Okay, we know the equations. Q is equal to minus Ka dt by dx. So that the same equations we have to apply here. Qx is equal to minus Kx dy dz dou t by dou x into d tau. Dou t by dou x into d tau. That we have to consider equation number 1. Okay, during the same time interval d tau, the heat flowing out of the element will be, by applying the Taylor series of expansion and neglecting the higher order terms. So we have to write it Qx plus Gx, that is present here. Qx is equal to what? And out of this element, heat is flowing out of this element, that is given by Qx plus dx. Qx plus dx, that we have to write by applying the Taylor series expansion. So that Qx plus dx. So that is present in here. Qx plus dx is equal to Qx plus rho delta dou Qx by dou x into dx. Qx plus dx is equal to Qx plus rho Qx by dou x into dx. This is equation number 2. Therefore, heat accumulated in the element due to the heat flowing x direction is equal to what? dqx is equal to qx minus of this qx plus dx. So how it is, when the this much amount of heat is flowing through this element, and this much amount of heat is leaving from this element. So this minus this will gives us the net heat accumulated within the element. Net heat accumulated within the element. That's why Qx minus of Qx plus dx here. Dqx, which is the net heat accumulated in the x direction, that is given by Qx minus of Qx plus dx. So here qx minus qx plus dou q, this term you have to write here, dou qx by dou x into dx, which is equal to, if you simplify it, this term and this term will get cancelled, this qx and this qx will get cancelled, and minus, we left with minus dou qx by dou x into dx. Okay, minus dou qx by dou x into dx. So here dx is equal to minus dou by dou x, minus dou by dou x. So again we have to substitute this term qx, which is there here. Just we have to substitute this qx term by equation number 1. So that is minus kx dy dz dou t by dou x d tau into dx. This dx is as it is. So qx, that is 10 from equation number 1, we have to substitute in this value, that is dou by dou x is as it is, qx value from equation number 1. Next, here simplify it now. Qx is equal to minus dou by dou x. Okay, dqx is equal to dou by dou x, minus into minus it becomes plus, kx dou t by dou x, so d dx dy dz into dou tau. It is equation number 2. Okay, so similarly, heat accumulated due to the heat flow by the conduction along y and z directions in time d tau will be. So if you get this equation, just instead of this x, we have to replace within y and z direction. So see here, dqx is the dqy, okay, d by dou by dou y. So here dou by dou x is there, just we have to replace that in dou by dou x, and here kx is there, and here ky dou t by dou y, here it is the dou t by dou x. Where there is the x term, that we have to replace it with the y term, that will give us the net heat accumulated in the y direction. Net heat accumulated in the y direction, that is given by dqy is equal to dou by dou y into ky dou t by dou y dx dy dz and d tau. This is equation number 4. Similarly, in the z direction, where there is z, you have to replace it with, if there is a y, we have to replace it with the z. dqz is equal to dou by dou z. So dou y is that, just you have to replace it with dou z, kz dou t by dou z in dx dy dz d tau. It is same for all these three directions. See here, dx dy dz d tau. Here it is a dx dy dz d tau, dx dy dz d tau. Okay, so all these three equations, uh, equation number 3 4 5, equation number 3 4 5 will gives us the net heat accumulated in the x y and z direction, okay. Therefore net heat accumulated in the element due to the conduction of heat from all the coordinate x directions, adding the equation number 3 4 5, equation number 3 4, and this is 5. Okay, so dqx plus dqy plus dz, all these adding all these equations. So whatever the term is there, see here, dou by dou x kx dou t by dou x dx dy dz d tau plus dou by dou y ky dou t by dou y dx dy dz d tau plus dou by dou z kz dou t by dou z dx dy dz d tau. Okay, and this is about the first term. This is, we get the first term, which is there here, net heat accumulated in the element due to the conduction of heat from all the three directions. That is first term. Up to this point is we get the first term, and the second term is the total heat generated within the element. So that is presented here, heat generated within the element. Okay, so that is given by qz is equal to small qg dx dy dz d tau. So that total heat generated within the element is given by the q small qg dx dy dz d tau. That is there here, dx dz dx dy dz d tau. That is equation number 7. Okay, this is the second term. This is our second term, where small qg is equal to heat generated per unit volume per unit time. That's why net heat generated within the element is given by this Q G into dx dy dz. This is the volume and this is the time. Okay, so here that is the second term. Now go on to the third term. Third term which is given by here, which is equal to energy stored in this energy stored in the element. So that we can get the third term, energy stored in the body is equal to mass of the body into specific heat into rise of temperature of the body. So energy stored in the body is equal to mass of the body specific heat into rise of the temperature of the body. That is, mass is equal to what? Rho into density into volume. So volume of that element is dx into dy into dz. Volume of that element side dx length into width into breadth. Okay, so that is mass of the body is given by rho into volume. That is rho dx dy dz. Specific heat is represented with the Cp, and the rise of temperature of the body is dou T by dou tau into d tau. This is equation number 8. Substituting this equation number 6, 7, 8 in equation number 1 here. So this is the equation number 1. Okay, substituting that equation 6, 7, 8 in equation number 1. So already we get that equation number 6 is here, equation number 7 is here. So that means what? Plus first term plus second term plus is equal to third term. That is, this is up to this point it is the first term, and this is the second term, and it is equal to third term. So whatever, first we have to consider three terms. So first we have to find out the net heat accumulated in all the directions. Second term, heat generated within the element, and adding these two will get the third term. Okay, so that is we have to substitute that 6, 7, 8 equation equations in equation number 1. So substitute as it is, you have to substitute. Okay, so dividing by the dx dy dz d tau on both the sides, because we are having the common terms here, dx dy dz d tau, dx dy dz d tau, dx dy dz d tau. So all these all the uh, terms we are in all the terms we are having dx dy dz d tau. So dividing these in all the both sides. Okay, dividing dx dy dz d tau on both the sides here. So we will have to with the dou by dou x into kx dou t by dou x. This and this will get cancelled. This and this will get cancelled, and dou by dou y into ky dou t by dou y plus dou by dou z into kz dou t by dou z, plus here only we will have to put small qg is equal to rho cp dou t by dou tau. Okay, this is our equation number 9. After dividing this to all these terms, we will get this equation. Okay, so next, using the Laplace operator delta, using the Laplace operator reverse delta. So here dou by dou x is equal to delta. Dou by dou x is equal to delta. So where there is a dou by dou x, we have to substitute this Laplace operator, that is delta. Here it is a dou by dou x is there, just we have to substitute that delta k into delta t. So dou t by dou x is there, so that's why it is a delta t plus a qz is equal to rho cp dou t by dou tau. So you see here, delta t is there, delta t is there, delta t is there. That's why we have to consider common delta t. So this is representing kx, ky, kz. If you write this kx, then it is kx, y, z. So in general, you can write this delta into k delta t plus qg is equal to rho cp into dou t by dou tau. This is equation number 10. Okay. In case of homogeneous and isentropic material, the equation 9 becomes, in case of the homogeneous, already we assumed that in our assumptions, the material, whatever the element we consider, that is the homogeneous and the isentropic material, then the equation 9 becomes, what happens here, the thermal conductivity is same because the material made of is same. So that's what kx is equal to ky is equal to kz is equal to, just we have to take it as a ky. Okay, the thermal conductivity is same. So that cases what happens here, dou square t by dou x square plus dou square t by dou y square. Here it is same, and dou square t by dou z square plus q g divided by k into rho cp by k dou t by dou tau. Just you have to substitute this kx is equal to ky is equal to kz into k here in this equation and take it outside. So divide it in both sides. That's we will get the equation number 11. Okay. So we know that the thermal derivative is alpha is equal to k by rho Cp. So that term is presented here. Alpha Cp by k is equal to what? Thermal conductivity alpha. Okay. So that you can write that dou square T by dou S square plus dou square T by dou S square plus dou square T by dou G square plus Qg by k is equal to instead of this rho Cp by k, we have to write that 1 by alpha, because the alpha is equal to k by rho Cp, but we are having that rho Cp by k, so that's why we have to write the inverse of that equation. So that is 1 by alpha dou T by dou T. This is equation number 12. So this equation is known as a three-dimensional conduction in Cartesian coordinate. Whatever the equation number 12 is there, that is our required equations for the heat conduction in Cartesian coordinates. Conduction equation in Cartesian coordinates. Okay, this is our final equation. And next we have to see the other forms of this equation by assuming some assumptions. When there is a no internal heat generation, so what happens if there is no internal heat generation in the element, then Q, this term is tends to 0. There is no heat generation, it is equal to 0. Then we left with only this term, which is equal to 1 by alpha dou T by dou T. Okay, 1 by alpha, because why it is this term is eliminated. When there is no heat generation, then u is equal to 0. Okay, or if you use the Laplace operator, then it becomes delta square t plus 1 by alpha dou t by dou tau. This equation is called as the Fourier equation. This equation is called the Fourier equation. Okay. Next assumption is steady state heat conduction. If there is a steady state heat conduction, then this term is becomes 0. This term is becomes 0. Then we left with only these two terms here. Dou square t by dou s square, dou square t by dou s square plus dou square t by dou z square plus q g by k is equal to 0, because the heat is in steady state heat. Then it becomes 0. When there is no heat generation, then this term is becomes 0. When there is a steady state heat conduction, then this term is 0. So again we have to write it in Laplace operator. Okay, steady state heat conduction without heat generation. Then these two term will get 0. So only we left with this one. Dou square t by dou s square, dou square t by dou s square plus dou square t by dou z square is equal to 0. When there is no heat conduction and also there is a steady state heat conduction. So it becomes delta t square Laplace transform. So delta t square by t is equal to 0. That we call the Laplace equation. This is the Laplace equation, this is the Poisson's equation, and this is the Fourier equation. Okay. Steady state one dimensional heat conduction without heat generation. Only one dimensional is nothing but dou square t by dou x square is equal to 0, because in these two directions it becomes 0, because only one dimensional. If it is two dimensional, then only we have to write these two equations. If it is only one dimensional, then we have to write only this equation. If it is three dimensional heat conduction equation in Laplace equation. Okay, so this is about the uh, general heat conduction equation in Cartesian coordinates, that is in rectangular cross-sectional area. Okay, so this is, and so in the next class we will start the three-dimensional conduction equation in cylindrical coordinates. Okay.